We begin our journey at the very edge of the known solar system, a frontier defined not by the familiar orbits of the planets, but by the frigid, distant expanse of the Kuiper Belt. We begin our journey at the very edge of the known solar system, a frontier defined not by the familiar orbits of the planets, but by the frigid, distant expanse of the Kuiper Belt. Here, beyond the gravitational influence of Neptune, lies a realm of icy bodies, relics of the system's formation, holding secrets of the deep past that remain largely undisturbed. Among these distant wanderers is Pluto, a world that exists in profound isolation, a celestial object defined by its remoteness and the vast emptiness surrounding it. For centuries, humanity gazed up at the night sky, charting the familiar dance of the planets. Yet the true scope of the universe remained shrouded in mystery until modern astronomy allowed us to look further. Pluto, once merely a distant speck, represented the ultimate boundary for exploratory reach within our own stellar neighborhood. Its location in the Kuiper Belt immediately presented a formidable challenge. Immense distances meant extreme travel times and incredibly faint signals, making any direct observation or physical exploration an almost insurmountable task. Pluto was not just another planet. It was the final outpost of our traditional planetary catalog, the last of the 9 worlds whose gravitational pull dominated the inner system. This status underscored the difficulty of its study. The sheer distance imposed limitations on how we could comprehend its composition or dynamics. To reach Pluto required technology far beyond what was available when humanity first began to probe the cosmos. The push to explore this remote domain was not merely scientific curiosity. It was an assertion of human ambition, a desire to breach the limits set by physical separation. It was a mission demanding tools capable of traversing staggering gulfs of space, confronting the silence and the cold of deep space to finally bring some clarity to the farthest reaches of our home. Pluto stood as the silent sentinel, waiting for a new era of exploration to unlock its profound, icy secrets. When we consider Pluto, we must also consider the limitations placed upon our vision of the deep cosmos before the age of modern telescopes truly illuminated the frontier. For centuries, Pluto remained a distant, theoretical point in the night sky, a remote speck residing in the sparsely mapped reaches of the Kuiper Belt. Early astronomical surveys offered glimpses, but these were not detailed views. They were mere hints, limited to simple color variations observed by instruments like Hubble. What we possessed were rudimentary sketches, faint impressions that hinted at surface texture, but offered no true comprehension of the world lurking beyond Neptune. The profound challenge for astronomers and explorers in this era was twofold: sheer distance and a lack of perceived significance. Pluto's extreme remoteness meant that detailed observation was virtually impossible with the technology available then. The vastness of space created an insurmountable barrier, making intensive study impractical. Furthermore, because the object held little immediate tangible interest compared to the familiar planets orbiting the Sun, dedicated, focused exploration of the outer reaches remained largely neglected. It was a realm defined by inaccessibility, shrouded in distance and obscurity. This historical context underscores the monumental leap that modern deep space exploration represented. The limitations of previous methods meant that Pluto existed more as an abstract concept than a tangible place. Only with the arrival of sophisticated probes, equipped with advanced sensors and propulsion systems, could humanity begin to bridge this immense gulf. These missions shattered those old boundaries, transforming the invisible periphery of our solar system into a landscape ripe for discovery. The transition from limited color data to high-resolution imaging marked not just a technological advance, but a fundamental shift in how we perceive the physical reality of the distant universe. The limitations of prior observation demanded a radical shift in approach. To bridge the vast distance between Earth and the remote reaches of the Kuiper Belt, humanity required a new kind of vision, a mission designed not just to observe, but to penetrate the deep space silence with unprecedented speed and detail. This necessity gave birth to one of the most ambitious endeavors in modern astronomy, the New Horizons mission. Conceived in the early 2000s, this endeavor was formalized as part of NASA's broader New Frontier program, an initiative reflecting a desire to push the boundaries of human exploration further into the unknown corners of the universe. The engineering challenge was immense, developing a probe capable of surviving the journey across billions of miles, navigating complex gravitational fields, and delivering pristine data from a destination no human eye had yet truly witnessed required groundbreaking technology. The core objective was singular and demanding: to reach Pluto as quickly as possible. Speed became the ultimate constraint, forcing engineers to optimize every aspect of propulsion and trajectory planning. This pursuit meant utilizing advanced techniques to exploit the subtle gravitational influences within the solar system, aiming to shave precious time off the long transit across deep space. The design phase was a complex interplay between theoretical physics and cutting-edge spacecraft engineering. Every component, from the launch vehicle systems to the navigation software, had to be calibrated for this extreme voyage. The goal was not merely a flyby. It was an immersive experience, ensuring that when the probe finally approached the distant ice world, the data transmitted would reveal the hidden secrets of its surface, a true map of an uncharted domain within the sprawling majesty of the cosmos. This mission was more than a journey to a planet. It was an assertion of human capability against the immensity of the deep space. To bridge the immense gulf between Earth and the distant Kuiper Belt, simple propulsion was insufficient. Reaching Pluto in the shortest possible time demanded a mastery of celestial mechanics, turning the journey from a passive drift into an active, calculated slingshot through the deep cosmos. The design for New Horizons was not merely a trajectory calculation. It was an intricate dance with the gravitational landscape of the solar system itself. To shave precious months off the transit time, engineers exploited the immense gravity wells of the giants. The probe utilized Jupiter as a monumental gravity assist, harnessing its colossal momentum to slingshot the spacecraft onto a faster, more direct path toward the distant destination. This maneuver was not a simple detour. It was a calculated gravitational nudge that fundamentally altered the speed and direction of the deep space voyage, transforming years into mere months. But achieving this ambitious trajectory required an equally powerful launch mechanism. The initial acceleration had to be absolute. New Horizons was launched using a fully boosted Atlas V rocket, pushing beyond conventional limits to escape Earth's embrace with maximum velocity. This combination of sophisticated gravitational maneuvering and raw thrust provided the necessary velocity to navigate the chaotic regions between the planets, allowing the spacecraft to punch through the veil of the outer solar system far more efficiently than any previous exploratory mission. It was a testament to human ingenuity, proving that even in the vastness of the deep space, the laws of physics can be harnessed to unlock the secrets of the universe. As the probe reached the orbital parameters of the distant Pluto system, the true challenges of deep space exploration began to emerge. The voyage itself was a triumph of engineering and trajectory planning, but the prolonged isolation required a radical adjustment to the spacecraft's operational protocol. to safeguard the delicate instruments and systems from the wear and tear of interstellar travel. The New Horizons probe entered a state of hibernation. This was not merely a pause in activity. It was a deliberate suspension of complex processes, allowing the highly sensitive hardware to conserve energy and protect itself until the moment of critical data transmission. Once in this dormant state, the focus shifted from velocity to viability. The next great hurdle was bridging the immense gulf of distance with the limited bandwidth available across the vacuum of space. Communication with Earth became a painstakingly slow process, constrained by the vast distances separating the spacecraft and our receiving stations. Data transmission faced profoundly slow uplink speeds, measured in mere kilobits per second. Each packet of information arrived after a significant delay, a digital trickle marking the passage of time between the distant world and the rapidly receding probe. This limitation meant that the raw data, the stunning visual details captured during the transit, had to be meticulously prioritized and compressed before transmission. The mission was no longer just about reaching Pluto. It became an exercise in extreme resource management, where every single bit of information had to be weighed against the constraints of physics and communication technology. It was a testament to the ingenuity required to translate the light and motion of the deep cosmos into meaningful knowledge, one agonizingly slow transmission at a time. As the probe finally breached the outer reaches of the Pluto system, the data that streamed back was not merely a collection of distant points. It was a window opening onto an entirely new reality. What began as sparse telemetry soon blossomed into stunning visuals, a slow, deliberate unveiling of the realm previously shrouded in the deep silence of the Kuiper Belt. Every few days, new images arrived, each one pushing the boundaries of what human eyes could perceive of this distant world. Initially, these views offered a stark comparison: Pluto, the primary target, and its larger companion, Charon. The evolving perspective revealed subtle yet profound differences between the two bodies, hinting at a gravitational dance far more complex than previously imagined. We began to see the true relationship in motion, understanding that they were not simply orbiting each other, but existed in a tightly bound, dynamic equilibrium within the vastness of the system. The detail grew with every transmission. The resolution increased, peeling back the layers of cosmic dust and shadow to reveal textures and contours previously invisible from Earth. These gradual revelations transformed Pluto from a distant speck into a tangible object of study, allowing astronomers to measure topography and map subtle variations in brightness that spoke volumes about the icy composition of its surface. And then there were the more fantastical hints emerging from these evolving views. As the camera swept across the icy landscape, patterns began to emerge, subtle anomalies that defied simple geological explanation. These were fleeting glimpses of shapes, structures that suggested intentionality, hinting at features so delicate and strange, they began to spark the imagination, whispering of an unknown geography on one of the farthest planetary bodies in our local universe. The growing collection of these images was not just scientific data, it was the genesis of a myth, setting the stage for the ultimate discovery of Arrokoth and unlocking the profound mysteries hidden within the deepest reaches of the universe. The proximity of Pluto to its largest moon, Charon, revealed a dynamic relationship far more complex than that observed in our familiar planetary systems. They do not orbit each other as independent bodies revolving around a common center. Instead, they exist as a tightly bound binary system, locked in a dance dictated by immense gravitational forces. The mathematics of this pairing challenge simple notions of orbital mechanics. The mathematics of this pairing challenge simple notions of orbital mechanics. When we calculate the precise point where the gravitational influence of Pluto and Charon balances out, that shared center of mass, or barycenter, is located surprisingly far outside the body of Pluto itself. This indicates that the system operates as a single entity, two worlds tethered together by a bond stronger than mere distance. This tight gravitational interplay results in a state known as tidal locking. Just as the Moon is locked in a perpetual embrace with Earth, Pluto and Charon are locked into an eternal embrace with one another. The side of Charon that faces Pluto is essentially always in contact, leading to identical day and night sides, both worlds perpetually oriented toward each other, dictated by their mutual rotation. This dynamic connection means that the internal forces shaping these icy worlds are profoundly different from those observed on larger, more solitary planets. The tidal forces exerted across this binary pair influence everything from the shape of Charon's mountains to the subtle flows within Pluto's distant heart. It is a system where two massive bodies have merged their destinies into a single orbital rhythm, pushing the boundaries of what we understand about planetary formation and evolution in the deep cosmos. This unusual configuration is not merely an observation. It is a profound lesson in the intricate mechanics governing the very fabric of our universe. The incredible data streamed from the New Horizons probe painted a picture of a world unlike any we had previously imagined. It was not a barren rock, but a sprawling landscape of frozen material, a realm defined by ice and shadow stretching across the distant night. The surface revealed by the flyby was a vast, cold expanse, dominated by what is known as Sputnik Planitia. This immense plain is not a simple feature. It is a colossal geological feature, an ocean of frozen nitrogen ice that blankets most of Pluto's visible surface. This nitrogen ice dominates the planetary body, making up nearly 98% of Pluto's total surface area. It is a substance that behaves similarly to water ice under extreme pressure and low temperature. Yet its sheer volume dictates a landscape defined by slow, deep, internal flows. This is not static terrain. It is a dynamic system shaped by the immense pressures within the distant cosmos. Sputnik Planitia itself is a feature of staggering scale. Spreading across Pluto's surface, this giant ice plain dwarfs many terrestrial features we know, comparable in size to the state of Texas. It represents an enormous, low-lying basin, a vast region where the frozen materials have settled and flowed over billions of years under the influence of gravity and internal heat. Examining this plain reveals layers and textures that speak volumes about Pluto's interior structure, hinting at hidden geological processes deep beneath the icy crust. The sheer existence of such a massive ice plain fundamentally alters our understanding of small, distant worlds. It shows us that even in the furthest reaches of the outer solar system, the rules of geology are still unfolding, governed by the relentless forces of physics operating across the silent expanse of the universe. This surface, frozen solid and ancient, stands as a profound testament to the dynamic, cold architecture of the deep space environment. Beneath the vast expanse of Sputnik Planitia, an unseen engine drives the slow, ceaseless motion of Pluto's icy crust. This is not a frozen, static world. It is a realm defined by dynamic ice physics operating under extreme cold. The material composing nearly all of Pluto's surface is nitrogen ice, and surprisingly, this substance behaves much like water ice, allowing for viscous flow over geological timescales. As heat from the interior interacts with the frigid exterior, this nitrogen matrix facilitates the movement of massive glaciers. These slow-moving rivers of frozen nitrogen carve the landscape, constantly reshaping the plains that dominate Pluto's surface. These glacial flows are evidence of deep internal energy seeking equilibrium within the distant cosmos. But the dynamics are not confined to the massive ice streams. When we examine the thermal patterns revealed by the New Horizons mission, we see intricate, shifting patterns across the surface known as polygonal cells. These cellular structures reveal active processes occurring within the ice itself, sublimation and convection currents. These convection currents represent the movement of heat rising from the interior and seeking escape through the atmosphere, while sublimation describes the process where solid ice transitions directly into gas. These forces create a dynamic interplay on Pluto's surface, demonstrating that even in the deep freeze of the Kuiper Belt, the physical laws of thermodynamics are at work, constantly influencing the fate of this distant, enigmatic world. The subtle shifts in these cells offer a window into the internal vitality of a planet existing at the very edge of our observable universe. But the exploration of the Pluto system was not merely about the dwarf planet itself. It opened a door to an entire realm of frozen matter lying far beyond its orbit, within the vast and mysterious reaches of the Kuiper Belt. It revealed that the solar system holds treasures beyond the immediate vicinity of the 8 major planets, objects held captive by gravitational forces in the deep cold of interstellar space. Among these remote collections lay Arrokoth, an object that defied prior expectations of what existed at Pluto's distance. Arrokoth was not a traditional planet or moon, but an enigmatic remnant, a captured asteroid that had spent eons drifting in the darkness before being pulled into Pluto's gravitational embrace. Its discovery by the New Horizons mission marked a profound shift in our understanding of the dynamic environment of the outer solar system. This object represented a frozen, pristine treasure, a dense core of rock and ice preserved from the chaotic formation of the early universe. When the probe approached, the unprecedented resolution revealed a landscape unlike anything previously imagined for an object in this region. Arrokoth was not a smooth, featureless sphere, but a complex terrain scarred by geological history, a tangible record of slow, icy processes acting over immense timescales. Its surface displayed intricate features, suggesting a history dominated by cold accretion and the slow grinding of ice over solid rock. This single discovery expanded our perception of what we consider a planetary system. It demonstrated that Pluto's influence extends far into the Kuiper Belt, binding objects together in complex orbital dance patterns. Arrokoth became a vital piece of the puzzle, illustrating the depth and diversity of matter residing in the deep space, where light travels across unimaginable voids. It reminds us that the unknown within the universe is vast, populated by frozen worlds waiting to be charted. The journey to Pluto and beyond was more than just a trajectory across the vastness of the outer solar system. It was an expedition into the very limits of what we believed was physically possible. The flyby of New Horizons did not just deliver images. It delivered a new perspective on the remote, frozen frontier that defined our understanding of planetary formation. We saw Pluto's surface with an unprecedented fidelity, revealing details previously hidden by the immense gulf of distance. The spectral data clarified the subtle shifts in ice composition and revealed geological structures that spoke volumes about the dynamic processes operating deep within this distant world. It was a demonstration that even objects situated on the periphery of our solar neighborhood hold complexity that rewards relentless curiosity. This mission fundamentally expanded our map of the cosmos by detailing the geology of Pluto and revealing tantalizing clues like the captured asteroid Arrokoth. New horizons dramatically expanded our understanding of the Kuiper Belt, that sprawling reservoir of icy bodies scattered far beyond Neptune. It showed us that the edge of the solar system is not a void, but an active, complex realm teeming with hidden worlds and mysterious interactions. The data gathered from this deep space voyage provided essential context for future astronomical endeavors. The successful navigation, the incredible endurance of the probe, and the clarity of the resulting images set a new benchmark for what unmanned exploration can achieve. This achievement proves that by pushing beyond conventional boundaries, we unlock new frontiers of knowledge about the structure and evolution of the entire universe. The legacy of this mission is etched into the fabric of modern astronomy. It transitioned the study of distant dwarf planets from theoretical possibility to tangible reality, establishing a new paradigm for how we approach deep space exploration. New Horizons stands as a testament to the human capacity to reach out and discover the secrets lying in the deepest reaches of the night sky. The journey continues, now armed with the knowledge that the outer reaches of the universe are far more richly detailed and mysterious than we ever dared to imagine. The journey to Pluto and the discovery of icy treasures like Arrokoth did more than just reveal new terrain. It fundamentally altered our perspective on the limits of our own celestial neighborhood. The data returned from the New Horizons flyby pushed the boundaries of current planetary science, demonstrating that the edges of our solar system are not empty voids, but complex, dynamic realms teeming with unexplored potential. We have glimpsed a fraction of the true story of this distant world, revealing intricate ice dynamics and hidden asteroids that challenge our understanding of formation and evolution. Yet, as we turn our gaze back toward the deep space, the revelations from the Kuiper Belt only deepen the mystery. The exploration of Pluto was an initial foray, an opening of a door into a vast, dark frontier. What lies beyond the orbital path of the major planets remains largely unseen, a repository of untold objects and unknown processes that define the true architecture of the local universe. This mission was not an endpoint, but a crucial waypoint. It proved that even at the farthest fringes of our stellar home, there is still profound discovery waiting to happen. The sheer scale of the universe, stretching into the deep space, reminds us that our knowledge is always incomplete. The findings from this deep space exploration serve as a mandate for future endeavors. As we look toward the next generation of missions, the focus shifts from mere discovery to sustained investigation across the entire expanse of the outer solar system. Future probes will continue to reveal the secrets of the Kuiper Belt and beyond, pushing the limits of what we thought possible for deep space travel and observation. We stand at the threshold of a deeper understanding. The mysteries held within the vastness of the cosmos are not solved. They are merely waiting for us to explore them further. The universe continues to unfold, inviting us to gaze once more into the silent depths, where the farthest reaches of our solar system still hold countless, profound secrets.